So a common question that comes up is dealing with intermolecular forces is actually how strong are they? So intermolecular forces are weaker than a covalent or an ionic bond. Hydrogen bonds are stronger than generic dipole-dipole forces for molecules of the same mass. Dipole forces are usually stronger than the van der Waals or London dispersion forces for molecules of the same mass. So I made this table to help give us some numerical values here to help us compare intramolecular to intermolecular. So remember, intra, this is like a traditional bond. Intermolecular has to do with the interactions between different atoms or molecules. So ionic, so example of an ionic substance here would be NaCl. So you have a sodium with a positive charge with a chlorine with a negative charge. So that's what's holding those two things together. Covalent, you're sharing the electron pair. So if you think of maybe carbon dioxide, the carbon is sharing its electrons with each oxygen. And metallic, this is the C of electron model is what's a metallic bond. So you have your cations located with a C. So let's say we have copper. So we have copper ions with excess electrons kind of floating around, making a metallic bond. The ones that you're most often going to see and discuss are ionic and covalent, because those are the ones that are easy for us to compare. So of these, notice how the ranges kind of all overlap. If we pick a number in the middle, so we'd have 2,000 here, we would have about 600 here, have about 500. Ionic bonds, generally speaking, are stronger than covalent and metallic. Covalent and metallic are about the same, generally speaking. Now, when we compare these to our intermolecular forces, if we do the same thing of picking a number in the middle, a hydrogen bond would be about 25. Dipole-dipole would be, about 15, and then about 10. So again, hydrogen bonding is still showing as the strongest intermolecular force with dipole-dipole and then London dispersion forces behind. So these are all interactions. So hydrogen bonding is a hydrogen bonded to NO or F, which are the most electronegative substances, while dipole-dipoles are permanent dipole. London dispersion forces are temporary. So I have examples drawn of both. Notice the positives are highlighted in the light blue and the negatives are highlighted in the pink. So a negative portion of one molecule is going to be attracted to a positive portion of another. Depending upon what's the electronegativity difference will determine exactly how strong it is. And we are able to calculate the strength. We just aren't going to take the time to do that because it's not helpful for our purposes. If you go on to take a more advanced chemistry course, it's something that you can do. And then London dispersion forces. This is something that happens in all molecules, but it's something that happens for a moment. So let's think of iodine for a second. I'm just going to draw one. Well, I'll draw two. We'll draw two. So iodine has a lot of electrons floating around. It has 53 on each of them. So think of the electrons in the outermost shell. So each has 7. So the electrons are rotating, are being shared between the two iodines. Because there's so many electrons, it's pretty likely that it's more likely than in something like hydrogen that you're going to have a London dispersion force. So you're going to have a temporary dipole occur. So for a moment, one of the sides is partially negative because it has an extra electron, and the other side is partially positive. If this happens in sync with another atom or molecule, there'll be a momentary attraction, but this isn't going to stay there. It's going to go back very quickly to the neutral state. Another thing I wanted to talk about with intermolecular forces is taking a look at the boiling point. One of the things that you can do is you can compare the boiling point with the intermolecular force strength. For something to boil, it has to overcome the intermolecular forces. So I have the boiling points here. Most of these substances are going to be a gas at room temperature. Water is, of course, a liquid, but everything else is going to be a gas. Room temperature in degrees Celsius is about 21 degrees Celsius. So if you had a really, really cold room temperature, you could potentially have a liquid hydrofluoric acid, but it's generally a gas. And then, so in order for something to go from a liquid to the gaseous state, it has to overcome what's holding it together. Some things that's very easy. Something like hydrogen or methane, they have extremely low boiling points, while something like water has a very high boiling point. So water has a hydrogen and an oxygen. So this is a hydrogen bond. Hydrogen and fluorine, another hydrogen bond. I'm just going to write H bond for abbreviations. And then nitrogen and hydrogen, another H bond. So these are the three main substances that will have hydrogen bonds as their intermolecular force. Now, the next substance, we have an H and a Cl. So it's not one of the three most electronegative substances, so this is just going to be dipole-dipole. And then methane, another hydrogen with a carbon this time. This is just going to be London dispersion force, and hydrogen is, of course, London dispersion force. So looking at the strength of these, water is the strongest. Hydrogen gas is the weakest. So you can kind of rank these. Now, let's say you were given two substances that had the same intermolecular force. Like, let's say you had ammonia, NH3, and water. And you were asked to determine which of the following have the stronger intermolecular force. If they provide you with the boiling points, the higher the boiling point, the stronger the intermolecular force is. So, the lower the boiling point, the weaker. So something like hydrogen is probably the weakest intermolecular force that you'll have. So if you look at the chart above, it said the weakest had about a 5. That's probably hydrogen's intermolecular force. While something like methane is a little bit higher, so it would require a little bit more energy to overcome it. So this is a potential type of problem that you would see being provided to substances that have the same intermolecular force but have the boiling points listed for you. The boiling points helps you to determine the strength. There are other ways for you to determine the strength. We're just not getting into them. This is kind of the easiest way to give a numeric value with it. So I have two visuals here. I have a flow chart. So I've added to your polarity flow chart. So this helps you to also determine your intermolecular forces. So a nonpolar substance experiences only London dispersion forces. Polar, you have to look to see if it's a hydrogen with NO or F to determine if it's hydrogen bonding or dipole-dipole. So, and then this kind of visual helps to illustrate each component. So every hydrogen bond also experiences dipole-dipole and London dispersion forces. We just focus on the strongest usually. Sometimes, though, I ask you for all of them. So something that's polar that is experiencing dipole-dipole is also experiencing London dispersion forces. And then, of course, London dispersion forces is only experiencing London dispersion forces. So in this outer ring, this would be all your nonpolar substances. In the middle rings, these would both be polar. So determining the polarity really helps you to determine what's happening with each molecule. Okay, so taking a look, I have 3 examples here. H2, as we've said before, is nonpolar. Only experiences LDF. So if you can kind of think of this, if you have a checkbox system, I have LDF, dipole-dipole, and hydrogen bonding. LDF is your weakest, while hydrogen bonding is your strongest. So for example, SCl2, this is something we looked at with your VSEPR, so you can take a look at the structure of it there. This is a polar substance. So it is dipole-dipole, that's the strongest, but it's also experiencing London dispersion forces. Every single atom or molecule experiences London dispersion forces. Doesn't have to experience it often, they experience it sometimes. And then NH3, we have a nitrogen with a hydrogen, indicating a hydrogen bond. But this also experiences dipole-dipole and London dispersion forces as well. So if it has hydrogen bonding, it experiences all three. Quite often we just ask you for the strongest. We don't ask you for all of them. But sometimes you are asked for what are the intermolecular forces that affect something. So it could be potentially all of them.